Hey everybody. So today we are starting our very last chapter, chapter 12. It's all on limits. Today we'll be talking about properties of limits. So first off, and we've done this before, this first section, like a lot of it, like the first part is just like reminding you what I've already taught you or what your teacher's already taught you up into that dashed line. So this whole part right here is review. Okay, so calculus definition. A limit of a function f of x is the number n that as x gets closer and closer to some number c but not equal to c, the corresponding values of the function f of x get closer and closer to n. So we have our own definition because that's a little wordy, maybe a little confusing. So the definition that we use is a height a function intends on reaching. So a couple things here. First off, height. So when you think of height on a graph, what value are we talking about? We're talking about the y value. So if the limit of your function does exist, the answer is the y value because it's the height the function intends on reaching. The other thing is this word intends here. If I say to you all that I intend on going to the grocery store tomorrow, does that mean that I went to the grocery store? No, it doesn't, right? It means that I'm heading towards that direction. That's what I want to do, but I'm not necessarily going to get there, right? So that's what you have to remember. If you are approaching a value both from the left and the right, and you don't necessarily get there, meaning that there's a hole in the graph, that doesn't mean the function does not exist. You're still intending on getting there, so therefore the value does exist. All right, how do we write limits? This is also a reminder here. So it's the limit. And then underneath there, in small script here, you have as x approaches, and then this will be a number right here, or a negative infinity or a positive infinity if we're talking about m behavior. So I'll just use c for any number. Right next to limit, the function's written, so it can be generic like f of x or g of x or q of x, or it can be the actual function, like 3x plus 2 or x squared plus 6x minus 5. And then you have the equal sign to show what it is, and then there'll be a number right here. Okay? Okay, so let's look at this graph right here. At every x value, there may exist a right-hand limit and a left-hand limit, and then the possible actual limit, and possibly an actual limit. The limit only exists if the left-hand limit and the right-hand limit agree. So when we're first teaching this to you, remember, we say like, what's the left-hand limit? What's the right-hand limit? Remember, left-hand limit is represented by this little negative to the right of number. Right-hand limit is this little positive sign to the right of the number. So what you're going to do is we're going to find how we did teach it to you is find the left limit, find the right-hand limit. If they're the same, that's the limit. Right, and then we kind of got rid of the left and right hand, but it is important that you know how to find those. So what we're going to do is we're going to find where 0 is. 0, where x is 0, is right here, right? So now what we're going to do is we're going to go on the graph. Let me change colors instead of using blue. We're going to approach 0 from what our graph's doing from the left. So I come from the left, and then you're getting closer and closer to 0, and you're going to say, what y value are you approaching? -2. So the left-hand limit's -2. Now you're going to approach from the right side. So we're going to come from the right towards the left. And you're going to say what y value you're approaching. It's -2. So since you're approaching the same y value from the left and the right, the limit as x approaches 0 is -2. Sorry. Make sense? Or recall, I should say. So this limit exists because the graph approaches the same number, the y value, from the left as it does from the right. For example, as f gets closer to x equals 0, f of x approaches -2 from both the left side, and as x approaches, I can't read, from both the left side of x equals 0 and the right side of x equals 0. So that's just repeating what I just said. Okay, so let's get on to somewhat of a new thing. This lesson right here that I'm about to show you, we actually taught it to you after we tested you we assessed you on limits. So it is now going to be in this chapter, okay? So there are 3 scenarios where a limit will fail to exist. So there's 3 situations in which a limit does not exist. 2 of them you've seen before, okay? So the first place a limit cannot exist, so right here, if you're looking at this, the limit does not exist where, okay? So if you look right here, we have the limit does not exist at x equals 2. Why does it not exist at x equals 2? Because if you look at 2, approach it from the left, you can see the y value you're approaching is 4. So if you look, the limit as x approaches 2 of, we'll call this function f of x, that's 4. Now if we look, oh, I'm sorry, that's the left-hand limit. Now if we look at the limit as x approaches 2 from the right side, if you look at what is the y value it's approaching, it's 3, or what looks to be 3. So since these 2 don't match, since they're not the same, the limit does not exist here, okay? So the limit does not exist at x equals 2. And the question is what is that called? When you have a point here and then no point right here and your graph continues again. It's called a jump, remember. So limits do not exist at jumps, okay? The next one here, this is called, this is when there's unbounded behavior, okay? So having no bounds. So it's not actually drawn in this graph, but what's in this graph that's not drawn in this graph because it's really what the graph is following and it's not part of the graph. An asymptote. It's actually missing 2 asymptotes. So you can draw them both in if you want to. So there's 2 asymptotes right here. This is a reciprocal function. So here, the limit does not exist at x equals -1. Because if you look at the limit as x approaches 1 from the left, I'll call it f of x again, and the limit as x approaches 1 from the right, these are 2 different values. So if we approach -1, sorry, it's supposed to be -1. Did I put that down there? I did. We approach -1 from the left. So here's -1 where this asymptote is. If we approach -1 from the left, if you say what y value am I getting closer and closer to, it's an arrow pointing upwards, so that's infinity. If you approach -1 from the right, what y value am I getting closer and closer to? Negative infinity. Since once again, these 2 are not the same thing, the limit does not exist. The last one here is when there's oscillating behavior, okay? This is what oscillating behavior is here. So if I say, what's the limit as x approaches 0? You're like, what is even going on there? Like it looks like a heart monitor that's going out of control, right? So this is called oscillating behavior, and limits do not exist at oscillating behavior. So these are the 3 places that limits would not exist. That is at a jump, at an asymptote, so this is asymptote, and then when there's oscillating behavior, okay? This is called a jump discontinuity as a reminder. This right here is called an infinite discontinuity as a reminder. Infinite, wow, I can't spell. And then that's oscillating behavior, okay? Now, another type of discontinuity that we've talked about is when you have a hole, which is called a removable discontinuity. That a limit does exist there. If you think about what a hole looks like, so let's say the hole looks like this, and then I have this line right here. If you're approaching that hole right there from the left and you're approaching it from the right, you're still approaching the same y value. So limits exist at holes. Limits don't exist at jumps, asymptotes, or oscillating behavior. Okay. Next, let's talk about basic limits and property limits. I'm actually going to skip basic limits for now, and I'll go back to it when we get towards the end of notes, because I feel like I don't do a good job of explaining it until I get down to this last part right here, solving limits analytically. Okay, so properties of limits. We're going to use the variables b and c in these, and we're going to use them as real numbers. So let n be a positive integer and let f and g be functions with the following limits. So here's one truth that I'm telling you. one given that I'm giving you, I'm telling you that the limit as x approaches c of f of x is the number L. And the limit as x approaches g of x is, as x approaches c of g of x is the number k. So we're going to talk about different properties here. So what if you saw the limit as x approaches c, and then there was something being multiplied by that function? So b, because I'm using b and c as my two numbers, I already used c, so of f of x. Okay, so if you wanted to know what that was, notice right here, I should probably put this in different colors. Let's see, what can I change this to easily? Red? No, it looks like orange. This is red though. Okay, so if you look at right here, you see the limit as x approaches c of f of x right here, which matches this yellow right here. So I already know that's L, so this is just b times whatever L is, and it's a property of it. Okay, sum or difference. So if I have the limit as x approaches c of, and it's sum or difference, so it can be f of x plus g of x, or it can be f of x minus g of x. I'm going to do plus or minus. And then that is equal to, so all you're going to do is you're going to take the limit as x approaches c of f of x, which is L, and add the limit as x approaches c of g of x, which is k. So this is whatever L is plus whatever k is, or if it's subtraction, then minus. Product, it's exactly probably what you think it is. Limit as x approaches c of, and if you have f of x times g of x, all that you're going to do is you're going to multiply their limits. So L times k. Division, same thing, they're same idea, I should say. Limit as x approaches c of, if you have two functions being divided, f of x divided by g of x, all that you're going to do is divide the limits. So L divided by k. And then the last one, power. So if you have the limit as x approaches c of f of x to the nth power, let's say, then it's just whatever the limit of as x approaches c of f of x is, which is L, and then bring that to the nth power. Okay? So let's try these 4 examples here really quickly. They're super easy. So on this one, I'm telling you, hey, just so you know, the limit as x approaches 2 of f of x is 7. The limit as x approaches 2 of g of x is 4. The limit is x approaches 2 of h of x is negative 2. I think I keep forgetting to say as x approaches 2, but I'm supposed to be saying that. Okay, so this says find the limit as x approaches 2 of 3 times f of x. So if you look at the limit as x approaches 2 of f of x at 7, and then you have a scalar multiplier of 3. So all you have to do is 3 times 7. So the answer is 21. Easy, right? This one, the limit as x approaches 2 of f of x plus g of x, is the same thing as the limit as x approaches 2 of f of x, which was 7, plus the limit as x approaches 2 of g of x, which is 4. So that's 11. Next one, I can break this up into the limit as x approaches 2 of h of x divided by the limit as x approaches 2 of g of x. So that would be negative 2 divided by 4, which we can simplify to negative 1/2. And then the last one, limit as x approaches 2 of f of x to the 3rd power. So I can take the limit as x approaches 2 of f of x, which is 7, and bring that to the 3rd power. So 7 to the 3rd power, 343. Okay? Okay, last topic, and then we'll go back before we actually do these. We'll do the first 2, 1 and 2, and then I'll go back and do the basic properties because they'll make so much more sense then. It says many functions' limits can be found analytically. Okay? So most of the time this can be done by substituting the x value where we try to find the limit directly in the function. This process is called direct substitution. So we have found limits graphically, but not analytically, okay? If you want to find a limit analytically, so find a limit here analytically, there's no graph, right? The easiest way to do it, if it's possible, which is going to be possible in all of these, is by using direct substitution. So taking this C value and substituting it in for X. Because then you can figure out what the graph is approaching. Because if there's a point there, then and it's approaching it from the left and the right, the graph is continuous, then that's the answer. So that's the first way that we're going to look at. Okay, so here, if I want the limit as x approaches 2, I'm going to do negative, and then I'm going to plug in the 2, square it, plus, plug in the 2, minus 2. All right, so I still have that negative in front. 2 squared is 4, plus 2, minus 2. So now I have negative 4 plus 2, which is negative 2, minus 2, and my final answer is negative 4. So the limit as x approaches 2 of my function is negative 4. Easy, right? So it's direct substitution. Once again, this is called. So I'm going to plug in 3 for x and see what I get. I get 3 times 3 minus 5 over 3 plus 3. Now, if the denominator is 3 minus 3, that's the different types of problems that we'll get into later. All right, so that's 9 minus 5, which is 4. 3 plus 3, which is 6. So that simplifies to 2/3. All right, let's go up to those basic limits, and then you can try the last 4 on your own, and we'll just compare answers. So here, the limit as x approaches c. We're going to solve these analytically to see what they're equal to. So plug this number in for x. So if I plug in c for x, there is no x. You get an automatic output of b. Here, if I plug in c for x, I get c. Here, if I plug in c for x, I get c to the nth. So really, if you know how to do it analytically, if you know how to plug something in, you should know how to do these. All right, this one here, you're going to plug in 4. The square root of 4 is 2. All right, we're going to try direct substitution. Plug in 3. 3 plus 1 is 4. Square root of 4 is 2. This one here, we're going to plug in pi. So we get pi times cosine of pi. So we have pi times, and now I need the cosine of pi. So think about where pi is on the unit circle. It's right here. Okay. What's that ordered pair? Which one is cosine? So we have pi times negative 1, which is negative pi. Okay, last one. If you haven't tried it on your own already, now you're like, oh, I see. Try the last one on your own. Pause the video. All right, plug in pi over 3. Okay, so this is pi over 3 times, and then I need sine of pi over 3 squared. Remember, sine squared of pi over 3 is the same thing as sine of pi over 3 squared. Okay, so I need the sine of pi over 3, so think about pi over 3. It's the same thing as 60 degrees, which is the ordered pair 1/2 root 3 over 2. The sine is the y value. So we're going to put root 3 over 2 here. And now I need to see what this is. So that's pi over 3 times root 3 squared is 3. 2 squared is 4. And then I can simplify 3 divided by 3. 3 divided by 3 is 1. So I get pi over 4 as my final answer. Okay, that's it for properties of limits today. So just make sure you know how to first try direct substitution, you know your properties, and then once again, the 3 places that limits do not exist, which are jumps at asymptotes and oscillating behavior. Okay, go ahead and get started on the homework. The homework tonight is a review for Chapter 10 to prepare for your final exams. This stuff that we covered here today will be on the next lesson's homework because it's so easy. We didn't give homework on it last year or the year before. We just always had the Chapter 10 final exam review as homework tonight. So go ahead and get started.